A warm good evening to everyone present here. I'm Naipunyadi, currently the CAS chairperson at NIEEE student branch. It is a great honor to have Mr. Dilip Rao as our speaker for today's session of the day 2 Illume, which is based on Introduction to Programmable Logic Devices. This session will be covering many topics on how PLDs go hand in hand with IC design, intricacies of FPGA design, emulation, prototyping, and even the latest trends in the field of FPGA technology. Before moving ahead, I would like to introduce the speaker of today's session. Mr. Dilip Rao is currently the principal engineer at NXP Semiconductors. He has an extensive VLSI industry experience, which encompasses all aspects of front-end chip design, uh, and his focus lies on emulation of low energy high bandwidth radio technology ICs. With this, I would like to hand over the session to Mr. Dilip, sir. So you can take it over.
Yeah, thank you, Naipunya, for a good introduction. Hi, everybody. Good evening. I hope I am audible and it's clear enough to comprehend.
Sir, you are audible, sir.
Okay, thank you. So this is a nice evening, and yeah, good evening to all. Before moving ahead, a bit of casual talk. Programmable logic devices is a very deep and intricate subject. Okay, so this is it's almost impossible to cover all aspects of it within a span of say 1.5 hour or 2 hour. It's almost not possible. So what I'm going to do is to limit the focus of this presentation mostly to FPGA devices. So there are several possible programmable logic devices in the market. I'm going to talk about them in the coming few slides. However, my current focus of this presentation will only be related to FPGA and how it's going hand in hand with IC design cycle, and how it's enriching our day-to-day life in the general sense, and also coming from an industry point of view, how it's critical for the success of any silicon, any complex silicon that is being implemented. Okay, so thank you for good introduction. A quick couple of words about myself. For myself, Dilip Rao, I have been working with NXP Semiconductors for almost 15 years now. So I have my field of work includes RTL design, synthesis, constraints development, then conventional verification methodologies, and the current field of interest is, as she mentioned, emulation, or you can call it as proof of concept of high-end transceiver radio frequency transceiver ICs, particularly those ICs implementing UWB technology. So that's where my current focus lies. A brief talk about NXP Semiconductors. So NXP Semiconductors is into this market of semiconductor design and manufacturing. It's a major player there. It has a significant footprint across all continents, and then it's majorly into consumer electronics, automotive industry, and then it offers wide ranging system solutions. It's not just the products that it is manufacturing and marketing, but it is also more about the end-to-end system solutions. So that is targeted for say smart city implementation, for example, say secure payment transactions, or access control mechanisms in a smart city environment. Or if you go one level below into the scope of a smart home, then you can think of all the various possible IoT applications that go for a smart home, bringing up a very intelligent and customized smart home experience, and also in the mobile space. So that's where NXP Semiconductors is coming into picture and is a major player there. Okay, I also am very happy to be here at this moment to be able to talk with you people. I would have loved to be there in person. However, because of the pandemic scenario and other restrictions in place, I'm unable to travel physically there. So that is something that I regret. But otherwise, I'm very happy to have this opportunity to talk with you people. So, see, this is my thinking. Being an engineer, right? See, it's always our duty to be able to communicate or interact with up and coming engineers like you, and nurture the budding talent. So that's one of our sacred duties. That is something that a way in which we can give back to the student community, and then in a way shape their future. So I'm very thankful for this opportunity to having presented myself with. So I definitely seek more and more such opportunities, and when this offer was offered to me, I was really very happy and grabbed it. uh, yeah, that's a brief background. Going to the next, let's start our deep dive into this topic. So this is a quick overview of the agenda that I'm going to talk about. Initially, I shall start with a quick overview of how the early PLDs. So PLD is an acronym for Programmable Logic Devices. I will give a brief overview of how the early PLDs evolved. It started in the 1970s to the current state where they are currently present. Very high-end complex architectures are supporting various high-end applications and working seamlessly with various other components and peripherals. So let us have a brief overview of how this evolution happened. Then the next, I want to share a platform that we are recently using in one of our products, and then I have a sample project, very simple code, just a flip flop, and just a register, and then I just want to show how that translates to actual hardware, and then I'll also talk about the current trends in the FPGA market or FPGA industry. So, just to understand briefly, I already had a talk with Naipunya. So, as I understand, the audience here is comprised of students. We have already have some background of VLSI design, and some section of the population who have no background. So, I will try to start from a very basic level and try to build the narrative to advanced concepts. The main idea here is I want to give you a brief peek or brief overview into what happens inside an industry. That is something that is not taught in your college syllabus, right? So you are mostly already well versed and well exposed to the theoretical concepts. So I will try to complement that knowledge with my understanding of what is happening in the industry, and that I suppose and I hope it helps you to prepare for your next career. Okay, some little disclaimers before we start. So, as I said, author, that's me, is just a facilitator here. It's not that I just speak and then you guys listen. No, it's not that way. This is just a facilitator here. I'm just trying to build up a good discussion point. So the the floor is open. Please feel welcome to ask your question. Nobody is perfect, including myself. So I may be wrong sometimes. So please feel free to interrupt me as and when you feel that something is not right, or something needs to be corrected, or you have a point to make. Don't hesitate, you can stop at me at any point of time. I will be more than happy. There is some vendor specific information that is quoted here. Okay, so that I have to mention that this is all the data that is present in public domain. There is no confidential data that is mentioned here. It's everything is there in the public domain that has been foraged, and that is presented here for a good understanding. So the concepts discussed here, none of them are my own brainwaves. They are the collective wisdom of several generations of evolution that these devices have seen. So I am not claiming any originality here. So that is why I don't have any hesitation when you said that you want to record the presentation or you want me to share the slides. I'm more than happy to do that. Okay, none of what is being discussed here is rocket science. It's all the next level of knowledge that you are seeking next to your college syllabus. Just one second, I'll just try to get my pointer. Okay. Okay, and then as I said, please feel free to ask any difficult questions. That is what is going to add value to the discussion. Okay, so this is not just a suggestion for this session. I will say this is my career advice to you also, because going ahead, that is something fundamental principle that you need to adopt. Meaning, you should always question what is being told. You need to apply your logical reasoning abilities to any fact or any information or any concept. Only then will you be able to learn and grow. Otherwise, what happens is, if you just accept what is told as a commandment, okay, this is what is needed to be done, and this, if you just go about doing that, we are going to get into an execution mode. Okay, so we are just going to be seen as the one of the many millions of engineers that the country has produced. So that is not something we aspire to be. As an engineer, I will say that you need to think, you need to question each and everything. You need to push the envelope, you need to question the status quo. Only then will you be in the innovative spirit. Otherwise you are going to get into execution mode. Then as a country, right, so we would like that. That's what an engineering spirit should be. You should be able to innovate. You should not be in an execution mode. We do not want to compete with, say, Philippines or Vietnam or countries like that. We want to compete with China. So that's the idea behind this advice to you. Programmable logic array. Okay, so then let's get started. Talking about the early evolution of programmable logic devices. So, programmable logic array, I suppose you already have heard about this in your maybe in the syllabus. Maybe or may not. I'm not very sure because this was part of MTech syllabus. I'm not sure if the BTech syllabus is upgraded to include them. Anyhow, so the programmable logic array is one of the earliest programmable logic devices which came into the market during 1970s. So here the idea is they have implemented a programmable AND array, and the outputs of this programmable AND array is then connected to a programmable OR array. Okay, so then this is going to implement any combinational function as a sum of product equation. Okay, so the programmability part is what is adding value here. Number of inputs are fixed, the outputs is also fixed, but you can program the device in such a way to establish the circuitry that you desire. Okay, so during fabrication, this entire device is fabricated with fuses among the gates, and when you want to configure or when you want to program, these fuses are selectively blown away. That is what the configuration means. The fuses are selectively blown to establish the desired circuit, and so consequently the necessary functionality has to be realized. Okay, so the current day PLAs can also incorporate flip-flops or registers to realize sequential logic, but in its oldest format it was just a cascaded connection of programmable AND array and programmable OR array. Then programmable array logic. So the name, if you observe, right, so this is confusingly named. The previous one was programmable logic array, but this one is programmable array logic. The name is little bit misleading, but however, here there is slight change in the architecture. You have a programmable AND array, and then you have following that, what you have is a fixed OR array. The programmability part is limited to the AND array part only. Okay, so it's easier to program here because you don't have to really bother about the fixed part here. The programmable part is limited, so that reduces much of complexity and the difficulty, but at the cost of versatility. So this entire device is not as versatile or as flexible as PLA, so that is reduced. But however, the cost comes down. Here we have lower size, and also this comes with a lower cost. So that's the value that it's going to bring here. That's what is quoted here. That's the value proposition. There are different value propositions that these two devices are bringing to the table. So we need to carefully analyze and be able to judge what is our current requirement and then pick appropriately. Okay, so in its oldest format, in the early days, this is what it was, but later day implementations also incorporated flip flops or registers to be able to build sequential logic. Excuse me. So the next device that I'm going to discuss here is a complex programmable logic device. So it stands for CPLD. This you can see as a next generation evolution of these PILs and PLAs. So here, as you can see in the diagram, it's basically interconnect of several PLA or PLAs arranged in a two-dimensional array. In a matrix format, you have several PLAs or PILs which are arranged, and then they are all interconnected through complex interconnecting routing resources. So this routing resources are programmable. You can program the routing resources to be able to establish the network of connections that you desire. Okay, so that way this is what is going to decide the functionality of the CPLD. This is slightly more advanced and complex than PLA and PAL, but this I will say is a the previous generation to the current day FPGAs. Okay. So the functionality for a CPLD can be defined using HDLs. This was not the case earlier. In the PLA and PALs, it was very basic and primitive functionality. You don't really need a the HDL language to describe the functionality. But here, this is slightly more complicated. So we need to describe the hardware functionality using HDLs, Verilog or VHDL. That has to be converted into a bit stream or what we call as a configuration data, and that configuration data will be programmed into the CPLD. There will be a non-volatile memory portion of this device, so that's the built-in E square PROM. So that device, that memory is going to hold the configuration context, and that is going to decide the functionality of the entire device. On power up, the configuration context present in the memory section will be programming the the macro cell and the PLAs, and also the programmable interconnect. It is called as a GIM, global interconnection matrix. So as to establish the necessary combinatorial and sequential logic and realize that in real hardware. So talking about reprogrammable world, right? So let us see what all the are the advantages that a reprogrammable hardware brings to us. So So it's something like reprogrammability basically actually means that the functionality is not hard coded. You're not limited to the functionality that is written and fabricated, but it is actually a fabricated IC whose functionality is open. It's a set of open unconnected gates. The functionality is decided at the field. So this is the the advantage or the luxury that programmable devices are bringing to us. So the main advantage here is that we have rehearsed your act as many times till perfection. Practice makes you perfect. So which actually means that there is no risk of losing the money if there is a design bug which is discovered quite late in the cycle. This is just a matter of reprogramming and re-downloading your configuration again into the device. So that's what is the benefit that we are having reaping here. Very less turnaround time involved. So here, as I said, right, so suppose you're going in the IC design cycle, so there are several distinct steps, each of them very expensive, and it comes with a very exorbitant cost. So anything gone wrong there is going to cost a lot in terms of energy, in terms of investment, and also in terms of your career. So however, that's not the case here. The turnaround time that is involved here is very minimum. It's like a software, so you're reducing your hardware functionality into a software. So suppose you have written a C code, and that C code all you need to do is to link and compile, create a binary, and then execute that. You discover there is a problem in that, so what do? You just go back to the source code. You don't really have to bother about money being lost. You don't really have to bother about the fabrication going waste. You don't really have to bother about time being lost. All you need to do is to go back, open your source code, look and fix the bug, recompile, relink, and then you have the binary again, and then you execute it. So this is exactly what a reprogrammable logic is doing to the hardware. So you don't have to really go back to fab to implement the logic again. All you need to do is to basically go back to the source code section, and then fix the bug or the problem that you have discovered, go through the run it to the entire cycle of steps again, and then build a bitstream, download the bitstream into device, and be done with that. So that's the benefit that we have here. Okay, so as I said, right, so here we have this luxury and we can afford to commit initial mistakes. It's not that every mistake comes with a very high penalty. That's the case for an SOC or an ASIC, wherein any small mistake is going to come with a huge penalty in terms of cost and in terms of energy and in terms of effort spent. Here, that's not the case. You can afford to commit initial mistakes. Nobody is going to lose sleep if the FPGA bit string is not working. All you need to do is to verify the functionality, discover the problem, go back to the design stage, fix it. Most of the times it's a problem in the design, and sometimes and very rarely it's a problem in the constraint, and then you need to go back to that stage, fix them. You need to come back and you need to build the bitstream, and then you need to download it, and you need to build the functionality. Excuse me. So the reprogrammable world advantage, right? So the reprogrammable advantage that we have here, as I said, how do we bring this benefit that we have here, or the advantage that we have in the reprogrammable world? That advantage, how do we bring it into an ASIC world? So as I said, right? So what we can do is use this reprogrammable logic devices as a prototype. Before you go and commit your millions of dollars into fabrication, you can actually show the proof of concept of your ASIC design. You can make sure that there is no mistake in that. You can actually validate, you can verify, you can make sure that your design is working well with other components like say software, boot ROM code, and other external peripherals. You can evaluate that on an FPGA, and only then, when you are 100% sure that the functionality is met in terms of say the timing, or in terms of the data throughput, or in terms of any other performance parameter, then you can go to a hard coded world. So that's how you bring the benefit or the advantage of this programmable logic into an ASIC world. Early silicon platform for real world applications. So that's what, as I said, this can be seen as a prefabricated silicon. An FPGA, if you see, is a prefabricated silicon. So you already have a silicon which is prefabricated, it's already available. It is just that the functionality is not hard coded, it's open. You can realize the circuit that you desire on the basis of the code that you have written based on that. So that's the advantage here. So this can be treated as a silicon before the actual silicon arrives, meaning you are going through an ASIC design cycle. There is a lot of steps, distinct steps, as I said, involved in that before you reach to a stage where you have a silicon. And when you reach that stage, you cannot afford to have any mistake. Okay, so that part you can push it into the pre-silicon stage. We can call this reprogrammable logic device to be a pre-silicon platform, wherein you can validate your design, you can validate your software, you can validate all the other parameters, all the other collaborating components which collaborate with your actual design to build a full system. So when you fabricate an ASIC, right, it's not just an individual IC, it's not just an individual product. It has to go and sit in a system and then perform the required functionality system to system, end to end. So that's how you build an ASIC, and that's how you go and sell it. Okay, so but before doing that, when you can what you can do is you can already fabricate that. You can already show the proof of concept of your design in an end-to-end system by replacing the ASIC with an FPGA, and then showing the functionality end to end. So that's where we can describe this to be an early silicon platform before even the actual silicon arrives. Okay, so what reprogrammability means in the actual chip design? So let's have a look at this. So, reprogrammable hardware, actually, what exactly it means, that you have, same piece of hardware, which is your FPGA device, for example, or it can also be a CPLD. So that same piece of hardware can be having multiple functionality, meaning based on the bit stream that you are downloading, it can implement, or it can demonstrate different functionalities based on the bitstring, or based on the logic that you are writing. It's a matter of just loading a new bitmap. So bitmap is a configuration data, is just a sequence of ones and zeros. However, it is derived from the actual logic that you have written in the source code. So you can build a bitmap based on the source code that you have written and download the bitmap. Every time you are going to download a new bitmap, this is going to, that is going to decide the functionality of the hardware. So that obviously, as I said, it can change every time. With a new bitmap, you can download a new functionality. It's just the same piece of hardware that's going to behave differently every single time. This is exactly the distinction that we have with respect to ASIC. In an ASIC, the functionality is fixed during the time of fabrication, so nothing can be done to change that. Not even a single cell can be programmed or changed in any aspects, and that's where the risk lies. Easy design changes. So when I say, right, that this, I think this we already discussed about this. When I say easy design changes, this is basically going to reduce the hardware complexity to similar to that of a software. If at all there is any problem or there is any bug that is discovered in your design, all you need to do is to go back to the design stage. Once you discover the bug and once you have the fix, you need to go back to the design stage. You need to see where the fix is going to get into the picture. Then you need to fix, you need to synthesize it, you need to take it to the place and route stage, and then you need to build a new bitmap, and then you have a new bitmap already done. So the design changes here is very easily done and not at all as complex as what we have for an ASIC. So faster development cycle. So when we have a reprogrammable hardware, we don't have to really bother about many complexities and many overheads that we have to otherwise bother for an ASIC design. So here the development cycle is very rapid. All you need to do is to go back to design and then build a new circuit and then download it into the device. So is the trade-off that we have to decide when we are going with reprogrammable hardware. This cannot go into a high volume production. ASICs or SoCs, right? They are intended for high volume production, wherein you have to fabricate millions and millions of those units to be able to break even and get profit. But because the cost of fabrication is so high that you need to sell in high quantities in high volume to derive profit out of it and make a business case. But that's not the case here. In the case of an FPGA, FPGA is anyhow not intended to be a final end goal. It is not intended to be a final ICE as such. So this is just used to complement the IC fabrication or IC manufacturing or IC design cycle, or it can be used as a proof of concept. I'm going to talk about different use cases of an FPGA in the coming slides. So this is not intended to be sold as an end product. So this is not intended to be sold as an end product, or it is not intended to replace an IC, and it is not suitable for high volume production. It can only be used as a demo vehicle. It can only be used as to buy more investment from your customers. Suppose you as an owner or as an entrepreneur or as an innovator, you have a disruptive idea, new idea. For example, say there is this video encoding algorithm called H264 algorithm. That's basically a video compression algorithm, and you have a patent on top of it. You have just discovered something that is going to change the way that's going to work. So this is is earth shattering idea that you have. You want to go ahead and you want to manufacture semiconductor implementing this idea, and then you want to make money out of it. That's the end goal of all the organizations or companies. They want to sell semiconductors and make money out of it. But for smaller companies, like say for example somebody is having a startup, or but he has a very good innovative idea. As I said, let us take example of say H264 decoder, video decoder, and then there is an idea that you have on top of it which is going to change the game. So what you need to do, but you don't have enough money or sufficient funds to go ahead and implement it and sell the units yourself. That's a very big business ask. You don't not everybody can get into that. So what you do, the best and the popular most easiest way for you to get this done is to implement your idea, or your enhancement design enhancements, whatever you have in your mind. You have to implement it in code. You need to build a netlist, you need to build a bit stream, you need to download it into an FPGA. FPGA is just as a vehicle here for proving your concept. That you need to prove that the concept that you have in your mind is capable of performing to the extent that you are claiming. So only then will people will come forward and invest their money and energy in your idea. Otherwise, just if you're going to, nobody is going to ready to commit millions of dollars just on the basis of some presentation and then empty talk. Nobody is fully sure enough to do that. You need to prove your idea to customers. Only then will they be able to come and say, okay, I am very interested in your idea. I'm sure this is going to be a game changer. I want to invest my millions of dollars into your initiating. So let's go ahead and bring out an ASIC and then let's sell them and make money. So that's how it works. So that's where this is only suitable for that space as a demo vehicle. You go there and then you prove that your concept is great. You have to prove that it doesn't break anything else. The enhancements that you have in your mind is working as intended in all scenarios and all possible of negative corner cases. Only then it opens the door for ASIC design. So it's not intended for a high volume production. It is not intended to be sold as an end product itself, but it is used as a vehicle to get going for the ASIC next cycle of ASIC design. This doesn't come with this NRE is basically a non-recurring engineering cost. It's a one-time investment that the companies have to do in terms of the research, development, testing, research, design, development, and testing of any products. So this is a one-time investment. It's usually very prohibitively high for any company to invest this. So that's what is called as an NRE cost. That's what I said, right? So ASIC design is a costly affair. Not everybody can get into this business. Usually, big players or the major players here, the companies which have big bucks, they can play around in this. They can innovate because they have the capacity to spend in R&D. Okay, they have the money, they have the resources to spend on R&D. They can innovate and then they can derive a business case out of it, and then they can make profit. So this NRE cost, right, that is not coming into picture if you are going with an FPGA or any other PLD for that matter. Why? Because this is already a prefabricated IC. All you're concerned with that is to download your logic or your digital design into that and then prove the concept. Okay, you don't have to spend millions of dollars on research, design, or development. All you need to focus is on what you're trying to prove. So that's where your focus will be centered on. Okay, so narrowing down our focus, let's see what is an FPGA. FPGA is an acronym. It stands for Field Programmable Gate Array. As I said, it's a prefabricated CMOS technology IC, integrated circuit, with unconnected gates. So the functionality is open. The functionality is defined and again programmable at field on the basis of what a user expects out of it. It is already pre-tested by the vendor. For example, if you're going and buying an FPGA from Xilinx, the Xilinx is going to have tested it already for manufacturing defects. So you don't have to really have the overhead of DFT logic there. You don't really need to worry about design for test. So design for test is a deep subject in itself. When you are fabricating an ASIC or fabricating an SoC, there's a lot of things that you need to worry about apart from the functionality itself. DFT is one such aspect. So when you say DFT, it stands for design for test. So this is basically intended to make sure that the manufacturing process is clean and there are no manufacturing defects that are being built into the flow, and the ICs that are fabricated or that are manufactured are usable at the customer site. So okay, so that's the whole idea of DFT. You don't really have to bother about that now because the IC that you are currently using has already been pre-tested by the vendors and the manufacturers. Okay, and then it can be used to solve any problem that is computable. What I mean to say by this statement is it can replace, any area where you are currently using an ASIC or you are currently using an SoC or you are currently using a microprocessor or you are currently using a hardware accelerator. You can just go ahead and replace that with an FPGA based logic, and then that is perfectly doable. So FPGA in a conclusion way, right? So FPGA is a high-end cousin of all these other programmable logic devices. For example, PLAs, we saw what is a PLA, we saw what is a PAL, we saw what is a CPLD. FPGA is, you can think of as a high-end and more complex and very more expensive cousin of these programmable logic devices. So the first commercial FPGA was out in the market in 1985. It was designed by a gentleman called Ross Freeman. He's a founder of a company called Xilinx. So Xilinx currently commands 37 to 38% of market share in the FPGA market scenario. So he was the founder of that. So it came, if you see, not very early. I mean, 1985 is still not so early as the other IC and transistor technology were evolving. So transistors and other IC aspects, right, they started evolving around 1950s or 1960s. But this FPGA technology is evolving only quite late, which is around 1985. So this has been in the field for comparatively lesser time, but it has evolved in a way so as to compete with now equally. It is now competing on an equal platform with highly capable ASICs and SoCs. So that growth, that what the FPGA technology has seen is very phenomenal. So how does it work? So how does it actually work? So yeah, you define what you want to define in HDL. Okay. So if it had been say a very primitive PAL or PLA, you don't need a HDL. You can just write some Boolean equations, and then you can have other methods in which you can download that equation onto those devices. But FPGA is a very complex, high-end application specific device. So you need to describe the functionality using HDL. You need to describe the hardware functionality in an HDL, like how you do for an ASIC or an SoC. And you need to compile the design to a netlist. So that is being done by a process called synthesis. So the inputs to the synthesis are the HDL code description plus the constraints. The constraints part includes timing aspects, and it includes area aspects, and other goals are there. And then you need to final end product of this FPGA flow is a bit stream. The bit stream, I think I already mentioned, is a sequence of ones and zeros which we humans cannot read and understand. It's going to program. It's the equivalent of a GDS. I don't know if you heard of this term called GDS. So geometric data stream. So GDS is an equivalent to what GDS is to an ASIC. This bit stream is to an FPGA. It's going to define the functionality, like what fuses are of outdated technology, but later we have SRAM based FPGAs. So this bitstream is going to define what parts are programmed in what way, what switches are on, what switches are off, what functionality is programmed into an LUT, and what registers are being used, what is a multiplexer selection lines, and in the essence how or what circuit is built into the device. That's being described by the bitstream. So the bitstream is then downloaded, and then that defines the field functionality. So there is no practically there are no limitations to the number of times you can program a device. It can stretch to many times. uh, there is no such limit. By the time you reach the limit that is mentioned in the spec or the data sheet, the device would have been outdated, and you would have anyhow had thrown out the device and then moved on to a later generation device. Where is it used? So I mentioned, I think, 3 4 use cases of the FPGA where it comes into play. Proof of concept. So you need to prove a concept. You have a innovative idea that you want to sell, because you want to go ahead and then make money out of it. So you need to prove it to the customers. Only then will they commit their money, and that's where you can use it as a demo vehicle. Okay, you need to measure system performance. You need to do this analysis of system performance. So wherein you need to define your IP, or you need to define your design in an FPGA. You need to build a full end-to-end system by connecting other peripherals along with this design, and then build an end-to-end system. And then you need to measure. There are several parameters. When you have a design, it's not just that logical functionality should be proven. There are several other aspects also. So the timing aspect, the timing score has to be met, meaning the design should work as expected functionally. The design should work at the expected speed in terms of clock frequency, and then the design should also support the necessary data throughput. For example, if you have, I was mentioning about H264 codec, it's a video comparison algorithm. So there are several parameters that comes with that. For example, you need to support the expected bit rate. You need to support the necessary resolution of the video clip. Plus, you also need to make sure that there are no pixels which are being seen by the end user, which means there should be sufficient data streaming all the time. There should not be any back pressure at any point of time in the data path. So that's the final sign off for the design. So to do all these measurements and do all this validation, to prove the sign off criteria, this we need to have an end-to-end system. For example, if you take a H264 video codec system, you will need to feed uh, real-time video streaming digital video into the system, then you need to have a video codec operating on an FPGA that has to be fed with the video stream, and then the video codec H264 codec on the FPGA will do the compression and implement the algorithm, and then this output needs to be fed into another video decoder, and that will be played it on a TV screen. So this is the complete end-to-end system. I'm just giving an example. Maybe there are some minor corrections in what I said, but overall point of view to understand this is what how a system looks like. So we need to build this complete system. We need to be able to validate that entire system in terms of performance, and only then we can say, okay, this IP or this video compression logic is working as expected. So that's where we need to have this proof of concept beforehand before you go ahead and come into a ASIC design cycle. Pre-silicon validation of an ASIC. So, ASIC, right, application specific integrated circuit, the current day trends, if you see, are highly complicated designs. So they come with lot of memory modules, very high speed. They operate at very high speed, clock frequencies. They come with lot of DFT logic built in, and then there is lot of possibilities or scenarios where things can go wrong. So we need to have a solid proof of concept of an ASIC before you go and fabricate it. That can be done using an FPGA. So you implement the design already on FPGA, and then you validate from an at least from an IP point of, if not from an IP point of view, you don't have to validate every sub blocks, because then that those things are already done in the verification environment. At least from a system use case point of view, you need to validate that the expected system use cases are working as expected, and then you can you have the necessary confidence to go ahead for fabrication. Then the last use case where FPGA comes into play is reconfiguration being required after deployment. For example, you have this use case, or you have this scenario where you are selling a product to an end user. However, that product needs to change either part of the functionality, or you may be memory contents. The memory, when I say, it can be flash or it can be any other non-volatile memory, the contents needs to be updated, or the functionality needs to be updated based on certain scenarios, or based on end user or based on customer. You need to adapt certain sections of the code. So in such cases, FPGAs are very popular choice. You can build this system using an FPGA, but again, that comes with it, the cost quotient, and also you cannot go for high volume production, but you can still use this FPGAs for this purpose, where you have to alter the functionality at field. Let me take a break, and then if you have any questions, please come forward and ask, because so far I have been talking and I don't hear anything back. You have any questions? Could be no question is foolish. Please feel free to ask whatever you decide to ask. Is it making sense, or is it a bit too much for the audience? Because I'm also a bit concerned about the skill set, or the the background that is needed for the audience. Because as I understand, there are students coming from no VLSI background, and also there are students who have some little extent of VLSI design background. So I do not want to be going overhead with too much of concepts here.
Sir, you can continue the session. As far as now, there are no doubts.
Okay. Okay, thanks. So, what FPGA is not? So, previous slide we were discussing what an FPGA is intended to be. Here we are saying what an FPGA is not intended to be. The FPGA is not intended to be a replacement to an ASIC or replacement to an SoC. That is not the intention. Neither can it be, because of the inherent limitations that I was speaking about. Right? It comes with its cost penalty, and also it's not intended to be sold in high volume like an ASIC. Okay, it's only used to complement an IC design cycle or an ASIC design cycle, or you have to prototype a complex ASIC. That's where this is coming into play. What it is not is and or plane based PLA CPLD. Okay, so this is not, it's not a PLA, or it's not a PL, or it's not a CPLD. They are all low end variants of this programmable digital circuits, which are of previous generation, or bygone era. The current generation of devices are highly complex and highly efficient, highly scalable. They are comparable with the latest, trending SoCs of today's market. FPGA is not something out of world concept. It's not a rocket science that requires complex coding guidelines, or complex design practices, or it doesn't require a totally different set of skill set or expertise to master. This is very much similar to ASIC, of course, but with little modifications compared to that, because of the inherent architecture limitations that we have in FPGA, which is not there in the ASIC. But those are very subtle and at a very high end level. So at a lower level, to start with, you will absolutely see no difference at all between an FPGA design cycle or an ASIC design cycle. Both of them look very similar at the ground level. So let's get going into the deeper, bottom layers of FPGA. So if you have a cross section of FPGA, if you take a cross section of an FPGA fabric, these are the basic building blocks that you see. You have LUTs, you have flip flops. I will speak in detail about what each of these components will implement. And then you have programmable routing resources. Basically, it's kind of a maze. It's kind of a maze, meaning two-dimensional matrix arrangement of logic element. Okay, every logic element at its lowest and very basic level will have a lookup table. Lookup table is a very easy way to implement a combinational circuit. And then you have also inbuilt flip-flops to realize sequential logic. So that's how a CLB is made up of. CLB is a configurable logic block. It's a very basic building block. I will talk in detail about that in the coming slides. And then see, this is the LUT I'm talking about, and then you have a flip flop here. This is how a CLB appears when you zoom into that. So this is a CLB. As you can see, the CLBs are arranged in a two-dimensional matrix method, and then there is a lot of routing resources which is running, a crisscross way, so interconnecting them. So when you have a bit stream, that bit stream is going to define the functionality of each of these LUTs. It's going to also define the functionality of this multiplexer, and then also decide what interconnection are active and what interconnecting resources are off. So that's it. That in a way is going to decide our functionality. Yeah, so this is just as what I was just explaining, a two-dimensional matrix kind of arrangement of configurable logic blocks. Then you have programmable interconnect, and then you have IO blocks. So this is how it looks like. So I'm trying to give to drive home my point, right? So I'm trying to compare each of these building blocks of FPGA with human anatomy. Okay, let's see what each every block, how each and every block compares or matches up with different units of our biology. So lookup table, I call them as the very lowest level, structures of the FPGA. I call them as cells, for example. Okay, so the lookup tables, as I said, can implement any combinatorial function. If you remember your digital electronics basics, you have this concept wherein a combinational function can be implemented, uh, can be implemented as a Boolean equation. So when you have a Boolean equation, what you can do is basically you can write a truth table for it. So the lookup table is nothing but holding the truth table for a combinational function. So the truth table is what is going to define the functionality completely, and that entire truth table is stored in a lookup table is going to implement a combinational circuit in the way that we desire. Okay, so this entire lookup for any combinational circuit that you want to implement will be translated into a lookup table, and that lookup table will be stored in the memory elements of the FPGA. That memory element of the FPGA could be ROM. There is no, so to say, there is no ROM in an FPGA. All we have is basically a RAM. Okay, so the ROM, you can realize a ROM, but at the base it is just a RAM with no write to port. That is what we call it as a read-only memory. No write possible, but it's called as a read-only memory. So if you want to implement a combinational circuit, what we need to do is to download this truth table into the memories built into the FPGA. So that is done inside lookup table. This is a good old LUT where you are storing all the possible output values for all possible input combinations. So that the truth table is being stored. So this LUT is right. If you see, it's not going to calculate the value of a circuit. What it used to do is to just retrieve by referencing the combination of inputs that is active at the current time. It is just going to read the lookup table and then figure out what is the output that he needs to drive, because these are the input combination that he is seeing active at that point of time. So the same memories that is going to implement the lookup table for a combination circuit can also be cascaded, can also be connected to implement 5 force and other memories. Other memories, when I say, it can be a single port RAM or a dual port RAM, or various other configuration is possible in an FPGA selection, IP selection GUI. So there are several memories that can be realized. So all these memories can also be implemented using these memory elements that is used to implement LUTs. So as you can see here, right, a four input combinational circuit will be having a truth table entries corresponding to 2 power of 4. Just as an example, I am saying. So similarly, in n input combinational function, we'll have a truth table entries corresponding to 2 power n lines. So to implement a 4 input combinational function, all we need to have is to store the possible output values for all the possible input values in those many lines, and that is what is a, the basic memory element of the FPGA. So if you go one level above this, right, moving one level above the hierarchy, what we have is configurable logic block. So configurable logic block is can be compared to the tissues, which is sitting one level above the cells in terms of complexity. So here it's a basic repetitive pattern. So it is arranged as I was showing in the previous slide. It's, a matrix kind of an arrangement where you have multiple CLBs which are crisscrossing the entire device, and then there is programmable interconnection lines which are running across the lines. These interconnection resources can be enabled and disabled based on our the bit stream what we have downloaded that there. So this CLBs, in addition to lookup table and in addition to flip-flops, will also have multiplexers, as we were seeing before in the prior slide, and it also has carry chains, which are implemented to implement complex functions there. So the CLBs are crisscrossing across the device, and they are connected through programmable interconnection switches. So these interconnection switches, right, they are also highly advanced, and they are proprietary to each vendor and very unique to that particular architecture. They can be switched on and switched off as desired in a very efficient way to interconnect these CLBs. CLB, configurable logic block, is Xilinx terminology, and its equivalent in Altera is basically logical array block. Okay, so they both of them essentially mean the same. It is just that the naming is slightly different based on the vendor. So here below is shown a very basic structure of a CLB or an LAB. We have, as a 4 input LUT. The output of the LUT connects to the input of a flop, and then there is also a clock and reset which is being fed into the logic cell or an element, and then the output goes out here. So this kind of structure will be repeated many million times throughout the device to realize our complex hardware that we are trying to program. So the routing resource, right? I have told before that I'm trying to compare the fundamental building blocks of FPGA with our human anatomy. The routing resource, I will compare it with blood vessels. So because the fundamental function of this routing resource is to be able to transport data by interconnecting CLBs across far-fetched corners of the device. So what these routing resources are going to do is to traverse the length and breadth of the device, and also transport by interconnecting CLBs from one section of the device to another section of the device. So this entire routing intelligence is constrained by our constraints, timing constraints, because the routing delays consume the maximum delay in any digital logic, if you see, right, the cell delays or the delays that is the signal has to consume, has to lose while traversing through a cell is very minimum compared to the delay that it takes in traversing from one portion of a device to the other corner of the device. That is, the routing delay is coming into play here. The routing delay takes a maximum hit that is going to decide, and that is going to limit the timing performance of the entire design. So it's very critical, or the crux of meeting our timing lies in making sure that the routing is done in a very intelligent way, and then so that we meet our timing performance. So this is entirely based on how good our timing constraints are defined. If we are defining the timing constraints in a very silly way, or in no, not in an efficient way, then the routing results also will be equally bad. So it is the onus comes to the the FPGA designer to be able to write constraints, timing constraints, and other placement constraints in such a way so the routing is achieving efficient results. So routing resources, right? As I said, there are several proprietary enhancements that are done by vendors. For example, Xilinx have their own way of enhancing routing possibilities, and Altera have their own way of enhancing routing possibilities. It's not just a simple interconnection matrix. I'm just trying to simplify it so that it's easy for you to grasp. But there is much more to it. There are several layers of complexity built into the routing. Okay, so there are several methods of routing. It can be continuous routing, it can be stacked or segmented routing. So just to give you two examples of different methodologies of routing, but there can be several layers of complexity there, which is finally hidden from the end user, because we don't really need to know. All we need to do is to decide, or is to define the timing constraints, and then leave it to the tool to achieve those timing results in the most efficient way that is possible. And in using its intelligence, it has to decide this is the best possible implementation of our circuit. Then there are routing lines are of different types. There are low skew global lines which run across the length and breadth of the device. They carry clock and resets, which are basically global signals, because they will be consumed by each and every cell of the design. Okay, and then there are long lines which interconnect CLBs which are far fetched and far away from each other. And then there is also local routing which are mostly used to interconnect CLBs adjacent to each other. So neighboring CLBs are interconnected through local routing. We don't need very high speed routing there, because they are sitting very close to each other. However, if you want to transport a signal from one end of the device to another end, you really go for high speed long lines which do not take too much of a diversions, and then go high speed line. So internal RAMs. So the current day SOCs, right? The current day SOCs and the current day ASICs. I'm sure you might have gone through previous presentation, the same forum where the complexities of stock design was discussed. So the current day SOCs and current day ASICs, right, they come with lot of complex requirement for memories. So the memories which are there, they are very essential for system to function. They are not only deep but also dense, and also there are very type and very technologies. For example, there are two main categories of memories: volatile memories and non-volatile memories. The volatile memories can be RAM, the very base. It can be SRAM. Okay, and non-volatile memories can be either ROM, which will hold the boot ROM code in a system, or it can be flash, which is going to have the next higher level of software, which is a firmware or a middleware. So these are the different types of memories which go to build a system. Then when you are prototyping such a complex system, you also need to have equally good amount of memories in your FPGA to match those requirements. Otherwise, it's not possible. I mean, that's a very inhibiting factor. So the FPGAs of today's generation come with large amount of memories inbuilt. Those memories are of two basic types. We can call them as block RAMs or distributed RAMs. So the block RAMs are dedicated memory units which are available throughout the device. They are very generously populated across the device. based on the logic, or based on the requirement, based on your constraints. Again, the block ramps will be used. It is highly parameterized. It will be highly configurable. They are available, at a very low resolution. They will be available. If you need to build a bigger memory, you need to cascade them accordingly. You need to be using multiple of them to build the memory with the width and the depth that you desire. Okay, and also, as I said, right, so these are the block RAMs, but there is also another method of instantiating memory. They are called as distributed RAM. So the distributed RAM basically are they are not the dedicated memories, but they are built out of the memories that are intended to be used basically for an LUT. Like how we were saying before, there are memory elements which hold the truth table for combinational logic. So they will be interconnected to build a bigger memory. That is what is termed as distributed RAM. So this naming, right? Again, this there is no common name which is assigned to the fundamental blocks of FPGA. It's very specific to vendor. Xilinx calls them with their fancy names, and Altera calls them with their own fancy names. But what is in a name? Finally, it's all the fundamentally. If you see, the functionality is the same. So integrated cores to build a full system, right? So these are what we call, these are what we going to term as organs. These are what we going to term as organs of our system. If you want to compare with our human anatomy, so it is not possible for us to define and describe every small functionality in terms of HD, every small functionality in terms of HDL. So what we need is basically an IP library wherein you can just instantiate different complex blocks. Commonly used complex blocks, commonly used subsystems are already made available to the end user to ease his design flow. So for example, the DDR memory controller, right? For example, the DDR memory controller need not be written or coded by every user who wants to use it. It is already available as part of Xilinx IP. Hi, do you see my screen now?
Yes, sir, it's visible.
Okay. Sorry for the interrupt. So to continue, integrated cores to build a full system. Okay, so I was speaking about the inbuilt IPs which are already available in the FPGA library. We can just choose to pick it and use it directly. You don't have to really go and build every possible digital block. So that makes our life much more simpler. There are two types of IP cores, hard core and a soft core. So the difference here I would like to highlight: hard cores are basically those IPs which are already implemented, which are already laid out, and they are already physically placed and routed already in the device. You don't have to synthesize it. You don't have to place and route it along with your design. Rest of the design, you can just choose to pick it and plug it with the system and start playing. It's like a plug and play IP. Okay, why it's already hardened is basically because of the complexity involved. As you can see, the hardened cores are very complex cores. For example, there are processors like Motorola PowerPC. It can be ARM Cortex in Xilinx devices. So there is no, the benefit is maximum if we can directly use it in its hardened form. If you're going to synthesize it, and if you're going to make a mistake there, or if it is not in an optimum way, then the benefit is lost. So that's the reason these complex cores are already hardened and they are available as hard cores. And then there are other cores like, for example, SERDES. SERDES is a serializer DC IP core, and then CDR. CDR stands for Clock Data Recovery Core. So these are all, as I said, right, again, high-end complex IPs which are available in hardened format. There are also some soft cores which are available. These are mostly low-end and simple IPs which can be subjected to user synthesis and user placement and user routing. So without much impact on their functionality, they are parameterizable, they are configurable, and they are available in the IP library. So you can just choose to pick and play. Okay. The examples of these soft cores include, clock generation blocks, or clock modifying blocks, or for example, the memory generator block. You can choose to implement a FIFO. You can choose to implement a single port RAM, a dual port RAM, or for example, say a debug features like an inbuilt logic analyzer, or virtual IO module So these simple cores are available as soft IP cores. These are, I would say, comparable with the organs of a human body. You don't have to build the organs every time; they're already available. You just need to plug it with the rest of your system and play. Okay, so this is a very critical part, right? So the crux of the entire design is the clock. So the clocks has to be handled with a lot of respect and love. Otherwise, it's going to goof up the system performance. So that's why I'm going to call it as a heartbeat. So the clock is very critical for the design meeting the timing and also making sure that the functionality is reliable and stable. So FPGA support built-in and balanced clock trees. There is no pain of laying the clock tree as it is in an ASIC. So ASIC or SoC, right, you are basically starting from scratch. That's what I said. The flow or the process is quite complex there. You need to get everything going from scratch, including laying out the clock tree, building the entire clock tree. You need to balance it. You need to make sure that there are no timing violations, and then you need to do a lot of physical verification in the backend stage, and then make sure that the DRC checks are clean. Only then you can go for fab. Here that's not the case. The clock trees are already laid. The clock trees are already balanced. All you need to do is to fit in your design to use the existing clock tree without breaking it too much. Sorry. FPGA devices, right? They come in with built-in DLLs or built-in PLLs for each clock tree. So DLL is an acronym for delay locked loop, and PLL is an acronym for phase locked loop. They are both identical in a sense. They are used for frequency synthesis. They consume an input frequency and then they synthesize it to generate, the desired clock frequencies. The desired clock frequencies can be multiple, or it can be divisor of the incoming or input clock frequencies. So the only difference between DLL and PLL is basically that PLL is based on inbuilt voltage controlled oscillator, okay, and a feedback mechanism. Whereas in DLL, what we have, we don't have a inbuilt voltage controlled oscillator. What we have is a delay line. Okay, so it's based on delay line. So the output of a DLL is having negative delay. So that's a major difference between DLL and a PLL. So as I said, right, the device's clock is a very critical aspect. So that has to be treated, with a lot of care. So the device itself is divided into several regions and sections, and each device and regions come with their own clocking resources, including DLL and PLL. They are populated with multiple DLL and multiple PLL. Based on where your rest of system is populated, you can decide to choose the necessary clocking resources in and around it. There are dedicated clock capable pads. Suppose you need to source a clock from an external world, or you need to feed a clock from the output of the system. You need to feed the clock through pads. Pads, when I say, they are the IO cells. So for to do that, to be able to achieve that, you need to have dedicated clock capable pads. Okay, so that feed or that connect directly to the global routing resources that I was talking about before. It doesn't help if you are feeding clock through a pad that is only connected to a local routing line. You need to have a pad that connects to a global routing line, so that the clock is transported to wherever you desire in a low skew and then high speed network. So board level clock DSKU. Suppose you are using the clock which is generated external to the device. You are using a clock that is coming from an external crystal or an oscillator that has to be DSKU'd, because the moment it is entering from an external world, again, the characteristics of a clock will be impacted. It will be coming with its own jitter. It will be coming with its own noise. It will be coming with its own ramp time being affected, slew rate being affected. So all these clock characteristics needs to be corrected. For that, we have specific deskewing elements which are built into the device. So their functionality is to clean up the incoming clock and make sure that a very pure clock waveform is fed into the rest of the design. So frequency synthesis is what I was talking about. There are specific DLLs and PLLs which do this. They consume an input clock frequency and implement a specific divisor and multiplication factors on that to achieve the necessary clock frequencies. For example, say FPGA, as I said, right, is a generic device. I mean, it's not possible that all the necessary clock frequencies are already there. My ASIC may need very precise clock frequencies of say some 50 hertz and 50 kilohertz and 50 megahertz. Somebody else, my neighbor, may be requiring some precise clock frequency, very accurate up till 3 decimal places. So it's not possible for FPGA, which is generic, offering, to be having all the necessary clock frequencies already in place. That's why what we need to do. That's why it comes with a frequency synthesis capable block. So the frequency synthesis capable block is capable of realizing very accurate and precise clock frequencies based on the dividing the divisor and the multiplication factors that you are going to program. Okay, so global and local clock buffers. So see, clock and reset is like very common and very highly used signals throughout the entire design that you are aware of. Almost every single flop in the design will be requiring to have a clock. It will be requiring to have a reset. So which means the clock and the reset has to be transported across the device through low skew high speed lines. Okay, so for that, naturally, what it will result in is high fan out on these nets, because it has to feed so many loads. There will obviously be high fan out, and then that is going to impact the clock waveform adversely. So to avoid that, what this FPGA tool does is it is going to intelligently insert clock buffers in the clock path, so that even in spite of being high fan out is taken care. I mean, you don't really have a case where one single line is feeding some 500 loads. That will never happen. It's going to have intelligently placed clock buffers where one line is duplicated, and then for feeding 500 loads, at least we have say some 10 or 20 or 30 identical clock lines feeding those number of loads. So that is what is the meaning of clock buffers. Then we have clock multiplexers. So clock multiplexers is a very critical resource in an ASIC design. There will be multiple clock and there will be several clocks coming into play. There may be a possibility or a scenario where clock switching is needed. Adding that kind of logical multiplexers on a clock path is not suited, or it is not ideal for an FPGA design. So that has to be handled. So for that, what the tool offers is basically a clock multiplexer in specific, meaning on the clock network itself there is a combinational logic which is implemented that is going to act as a multiplexer. Instead of writing a logical multiplexer, you can just choose to instantiate the clock network multiplexer to avoid inserting skew to the network. FPGA, or it can be, as I was mentioning about example of a video codec, it can be a input video stream, or it can be feeding the compressed video data into the video decoder, which will then be connected to a TV display. Just to give an example. Okay, these are what we call as user IOs, going to provide connectivity for your system with the rest of the world. So uh, current day devices, if you see, right, there are thousands and thousands of user IOs. This is also one of the criteria that we need to consider when we choose an FPGA device. We need to choose it in such a way, we need to select in such a way that it meets our requirement. For example, if your system is going to have say some 300 or 400 pins, and you have selecting a device which has hardly 50 to 100 pins, then that's not going to make it. So while you are selecting a device for your FPGA prototyping activity, what you need to have is to have the, let's say, a set of requirements that are absolute must, and then you need to match that with the offerings of the FPGA device, family architecture wise, or maybe IO sensors wise. So only then you need to make a good selection. So these IOs, right? So these IOs are going to implement or equivalent to the IO cells of MSIC. So they are possible to support several signaling IO signaling standards. So it can be differential standard, or it can be single-ended standard. And there are several possibilities in that. There are several possible signal standards which are defined in the protocol point of view. It can be LVDTL, it can be LVCMOS, it can be LVDS, it can be HSCL, or it can be any other examples. So there are multiple standards which are being supported based on who is sitting on the other side. So you can have a device which is operating on LVDS interacting on one side with your system. On the other side, you can also have a device which is operating on LVCMOS, which is a single-ended standard. So that's also possible. So for that, what they have done is IOs, right? The IOs of an FPGA are divided into several banks, and within a bank, they support a particular signaling standard, and the next bank will support the next signaling standard, some other signaling standard. So this segregation is done to be able to achieve and talk with multiple peripherals simultaneously. The IOBs, right? IOBs can be configured as input, it can be configured as output, or it can also be configured as a bidirectional line. A bidirectional line is basically a tri-stated buffer implementation, wherein you can switch from being an input, or you can also switch from being an output, and vice versa. On the fly, based on certain selection lines, you can switch from being an input and from being an output, and bidirectional way. So this, just to summarize the anatomy of the FPGA that I have discussed so far, LUT flip-flop pair, that is sitting at the very lowest strata of existence. So that's the very basic cell. I call it as equivalent to human cells. Okay, then we have the next. If you go one level above the hierarchy, we have these micro level logic blocks. I call them as tissues, comparable to human tissues. So as I said, it's called as configurable logic block by a vendor, or it can be LAB by some other vendor. But in the true sense, it's basically a mixture of LUT, flip flop, carry chain, and a multiplexer. Many of them. The routing resources. So when we say routing resources, what we have is basically the connecting resources that can be connected across the device, from being from one portion of the device to another portion of the device. This is again based on our constraints and our pin constraints in particular, because we might have mapped certain fundamental signalings to particular pins, so that has to be respected. These are the routing resources that are comparable to blood vessels. So and then we have these ramps, which are basically memory units. So this I will compare to neurons in our brain, which retain, which help us memorize information. The most critical part of it, the clocks, which is basically the heartbeat. This is going to be critical in improving the functionality. And then we have these IO blocks, which are basically the sensors, which are going to which is going to connect our logic with the rest of the world. Finally, the configuration. Configuration, when I say, is our circuitry that you have foreseen, that you have in your mind, that you have coded, that you have synthesized, you have placed, you have routed, and you have the bit stream. So that's what is going to define the configuration. So this is giving life to the human. So why I compare this, a programmable logic device with a human is basically because both of them, if you see from a high level of abstract, so the humans, the way they are today, is also the result of many millions of generations of evolution. We are not looking like monkeys anymore. Okay, we don't have a tail because we don't really need a tail in our day-to-day life. Instead, what we have grown is we have grown our brain size. Why? Because that's what is helping us to survive and thrive. Similarly, the programmable logic devices, right? If you see, they started as a interconnection of programmable and or elements. But if you are still there, then that's not going to help. You also need to scale up. So that's what has happened there. This evolution, innovation, and scaling up has happened. The current day FPGAs, if you see, they're comparable with the best of the SoCs that are currently being pushed into the market. So, a brief comparison between what we have for an FPGA versus what we have for an ASIC, because I think being students at this stage, you would be a little bit in a confusion state as to what exactly is the difference and how to fit that, where these differences map to. So, this is the table I would like to go through. So, if you see, right, the time to market for an FPGA is quite fast. If you see, the tab is longer here, so the time to market for FPGA is very fast. You don't really need to worry about a lot of other overheads that come into picture for an ASIC. For ASIC, it's a bit slow because you need to worry about hazard other things. Otherwise, you are going to ruin your money. Okay, so for the factors that we have already described before, I will not go through that again. And then non-recurring engineering cost is also something that I discussed. So it's low on the FPGA side. It's high on the ASIC side. Design flow, is quite simple on the FPGA side because most of the complexity is hidden behind the tool. You already have a prefabricated IC. Okay, you don't have to really break your head to get it going. All you need to do is to make sure that you have a decent design, you have a decent set of constraints, and then you are done. That is not the case for an ASIC. You are building everything from scratch. There is no fabricated IC. There is nothing there. So you need to build everything from the scratch. That's the reason why the design flow is a bit complex on the ASIC side. The unit cost, also, I think I spoke about this. The unit cost is very low for an ASIC. If you see the most complex of them, hardly costs a few cents. Why? Because their business value lies in the millions and millions of units that are being sold. Okay, even it's priced per unit to be very low. The business value comes. The profits are seen when you sell them in millions and millions. That's what the value proposition is. But for an FPGA, that's not the case. As I already mentioned before, we are not going to make it as an end product, and we are not going to market it similar to ASIC. This is just used as a demo vehicle, just to unlock the door of a plethora of possibilities for further ASIC design. So here the cost per unit is very high. To give you an example, right, a medium size FPGA will cost you, or easily cost you, more than 5 to 6 lakhs. So that way, right, it's very expensive per unit, and it is not supposed to be sold in millions and millions. Okay, that's the reason why they price it very high. That's the business proposition of the vendor. Otherwise, if they are going to sell it in a matter of few cents, they will never be able to recover the the cost that they have invested to get that into market. Medium, the performance, right? So performance, as I said, this is a generic platform. It is like one size suits all. That's the concept here. It's a very generic platform, and then you need to derive the maximum out of it. So it comes with the penalty. The penalty or the cost that you are paying here is basically there are some performance limitations that you cannot overcome. Okay, because what you are trying to do is to fit your design into existing infrastructure and derive the maximum out of it. Whereas in here, on the ASIC side, you can build anything from scratch to suit your specific, as the name says, right? Is application specific integrated circuit. Is a hard coded design built to meant for a specific application. That's not the case here. Okay, that's the reason performance takes a hit. That's the trade-off that we have to do. That's the trade-off that you need to consciously decide. Power consumption, we don't really bother about power consumption for an FPGA because FPGA kits, if you have seen, they always come with battery, or they are always connected to power. Nobody is worried about power consumption because finally it is not going to end up in the market. However, for an ASIC or an SoC, that's going to end up in various power hungry or power critical applications. Say for a mobile phone, if a mobile phone is draining out battery every 2 hours, nobody is going to buy that. So that's the reason why power is a very critical thing in an ASIC design. So you need to be very careful there, and you need to limit the clock switching. For example, you need to design keeping in mind the low power design techniques. That's a completely different, very deep subject. I will not get into that. Those things need not be bothered for an FPGA design. Okay, and then unit size. Okay, unit size. For example, unit size. If you see the ASIC, right? ASIC again comes with its own. It has to meet its own criteria. Otherwise, it's not going to sell. So size is one such factor because the size it's going to occupy on a PCB is a matter of grave concern for the end consumer, because that's finally going to decide your system size and also the fabrication cost. So nobody is going to buy. You go and intend to buy a phone. The phone has to be compact and it has to perform at the higher end. So if you go intend to go and buy a phone and instead you are offered a tab and say that this is exactly same features that you are getting in the phone, nobody is going to buy that. So that's a rough example I wanted to quote. So continuing this discussion, right? FPGA versus ASIC design flow. Just a brief description of the differences in that design. So what we saw before is at a much higher level. What exactly is the difference in the value propositions of ASIC and FPGA? But here we are getting deeper into the design flow. So front end flow. So the design flow, right? Design flow is divided into two distinct portions. One is called as a front end, other is called as a back end flow. So the front end flow extends up to the synthesis stage, starting from design entry in HDL, and defining the constraints and verification and synthesizing. That's makes up the front end flow. The rest of the steps, right, excuse me, the rest of the steps makes up for the back end flow. The front end flow, at least up to synthesis, is very much similar between an FPGA and ASIC. So as I mentioned before, FPGA is not rocket science. It's not something very different out of this world. It's very similar to ASIC design, at least from a front end point of view. Backend flow, it's a similar, but as I said, it's much more complex in ASIC because there is a lot of other overheads that creep in. For example, you need to worry about DFT, you need to worry about power, you need to worry about so many other things, clock tree, for example. So all these overheads are removed in an FPGA. We don't even have an analog implementation. FPGA are purely digital, so the major complexity is gone there. Okay, so the backend flow is much more clean, it's much more straightforward, it's much more similar, and the complexity is hidden behind the tool intelligence. End user need not really bother about how the tool actually goes and fix a hold violation here in FPGA. But for an ASIC, it's very critical to analyze each and every violating path, and you need to have certain amount of judgment and consciously decide how to go and fix a timing violation. That part need not be really consciously handled here. DFT, as I said, I think I mentioned before. So the device is already prefabricated silicon. It's already tested for manufacturing defects. You don't really have to bother. That's not the case for an ASIC. It has to be built from scratch. DFT is a big portion of the investment in terms of effort and energy on board. So once you have an AC out of a fab, you don't have to really bother about downloading the configuration or downloading about programming that part, except programming the non-volatile memories, which is definitely the case. However, for an FPGA, you need to be having a configuration data in terms of bit stream, and that has to be programmed once the device is powered up. So now we are going to discuss a bit about why we need to prototype in ASIC, why we need to bring in FPGA into an ASIC design cycle. Why can't we just go ahead with the ASIC design cycle as it is? Why do we need to have this extra complexity in terms of FPGA design and prototyping and proof of concept? Why is it needed? As I said before, I think throughout this discussion I said many times. So before we go ahead and commit the huge amount of investment that is necessary for ASIC design, it's very crucial that we have a working silicon already. So that's where FPGA is coming into picture. We need to verify, we need to validate the design that it's clean before fabrication. There's the extra confidence that we seek here. Okay. Several aspects here. See, there is a verification domain. There's a verification. So ASIC design is quite complicated, as I said. So there are several adjacent domains which are coming into play. Verification, for example, is one such thing. Okay. So the main idea of verification is to catch functional bugs before the silicon arrives. However, verification can never be hole free, or there will always be a possibility in which there is a bug which has escaped verification. Okay, that's always a possibility. So those bugs need to be caught in real time on FPGA. Okay, that's the purpose of one critical requirement for an FPGA. Okay, so why and how, I think a little bit deep. I will not go into that, but definitely the holes in verification needs to be covered in pre-silicon validation. And then the preparing validation infrastructure. Once the silicon arrives, that has to be tested thoroughly, not only for manufacturing defects but also for functionality. So that is a big task in itself. It's a big ask. There's a lot of test cases that needs to be coded. There's a lot of environment and scripts that needs to be developed. You cannot wait until the day silicon comes and then you can start on that day. No, not possible. You're going to lose a lot of time there. So what people do is to start beforehand using FPGA, because there's also a silicon already in advance. So they are going to use this platform to build the validation software, flow, environment, and scripts, and also build in the necessary automation, so that the moment we have the silicon available, it's just a click button for them, and they're going to execute the tests. And then if everything goes clean, then you're going to save a major effort there. Reduce the time and effort in post silicon validation. The same thing as I was just mentioning. You don't have to wait until the day you have silicon is fabrication fabbed, and then you have it and only then you start validating. You can already start it much before, so that you save on the unnecessary time and effort. Because The time to market is the key thing in any semiconductor design. Time to market is a key thing. So you need to be the first to market. Whoever arrives first to market captures the major share of the market, and he is the winner. Okay, so that's the fun. Complement verification with added scenarios and coverage. I mentioned before, the validation is supposed to catch those scenarios or those. The simulation time, right? Again, there is a difference here. There is a difference between simulation time and there is a difference between real time. What we have in verification is virtual. What we have in validation is real time. Okay, so here we have actual boot ROM. Here we have actual software. Here we have actual, host processor, for example, or another components which are interacting with the system. That's not the case in a test bench. It's all virtual world. So it's possible that multiple scenarios which are passing there can still fail here to uncover the bugs which are missed out. This one I think already mentioned. So you can already start on working, developing the higher level of software, meaning the firmware, already ahead of silicon. Okay, in the benefit of time, I will just quickly run through this. So these are the essentials of emulation of an ASIC. There are several aspects that you need to consider. You need to select the correct, based on your judgment. You need to select the most efficient, cost-effective, and then the fastest available FPGA prototyping platform. You need to partition the design accordingly. For example, this is slightly not applicable for current trend. This was the case sometime before. For example, if you have an ASIC which is much highly complex, and then the gate count of an ASIC several times that of what an individual FPGA can absorb. What used to happen was we needed multiple FPGAs to emulate a single ASIC. So what used to happen is we need to partition the design in an intelligent way, that the signals traveling across multiple FPGAs are partitioned suitably, so that you're not losing timing. You're not hit on the timing part because of your wrong partitioning. You need to partition the design appropriately in an intelligent way, so as to make sure that the interfaces crisscrossing across external devices are all low speed, and then you're not partitioning it the wrong way, which will result in high speed interface being broken from one FPGA periphery to another FPGA periphery. So that's the importance of FPGA partitioning. Then you have implementation, synthesis, and place and route. Okay, so yeah, so this is again a very wide, very deep subject. So this discusses about the complexities that we encounter during synthesis stage, or maybe the place and route stage. So we need to be able to solve that specific to the FPGA scenarios. Timing closure is a key challenge here for FPGA, because, as I said, right, so you're trying to fit in your design into the existing network, into the existing set of resources, into the existing set of architecture. So that will not always work. So you need to have, you need to live with certain limitations that come with that, and then you need to still be able to make the most of it. So that is again a trade-off and a balancing act which comes with experience. Vendor family and part selection. So this thing, right, so this thing, as I said, when you decide to prototype, or when you decide to proof of concept your idea, you need to make sure that you have selected the correct device, correct family, correct vendor, and correct architecture based on your design requirement. For that, you need to do a deep you need to have a deep understanding of the device architecture. You need to understand the complexities involved, whether that can sufficiently support your requirement. So that's a good study that you need to spend time on, and based on that you need to proceed. There are a lot of factors which come into play here, uh, but in the interest of time I will skip them. This is quite detailed. So design entry stage, right? So design entry, when you have a soft design that needs to be fitted into an FPGA. So this is not going to be a click button job. It's not a very smooth thing to do. You need to be having the intelligence enough to make the necessary changes. The changes sometimes will be very obvious. Sometimes the changes will be subtle. So you need to make sure that you have taken care of every aspect. Only then you can fit an SoC design completely into an FPGA, because FPGA, right? I mean, it comes with its own architectural limitations which are inherent and which are inbuilt into that. Nothing can be done about that. So we need to make sure that the design is customized, and then modified in suitable way so that it can be programmed into an FPGA. For example, as I have talked before, clocking strategy is very different here. It's not exactly like how we have for an ASIC. It's not built from scratch. We need to try to fit it. DFT logic needs to be switched off. You have an SOC database. In that SOC database, the application mode and DFT mode sit hand in hand. They are always going hand in hand. They can be enabled selectively, but that's not the case here. We need to completely be able to kill the DFT logic to save on the logic resources, and also gain some advantage in terms of timing for the application mode, because our intention is to only prove the application mode and not get into DFT mode. So all the hard instances have to be replaced. When you get into an ASIC design, you will see that ASIC is targeted for a specific technology node. So there will definitely be several technology specific cells that are instantiated. So those things needs to be replaced here, because the technology here is totally different to compared to what we have for an ASIC. We need to replace them with suitable behavioral model. Clock gating we has to be handled differently. As I said before, clock gating directly contributes to power saving, and so clock gating is very crucial for an ASIC. For an FPGA, we don't really bother because power is not at all a matter of concern. So clock gating can be completely switched off. We don't really until unless it's a functionally important clock gate, we don't really have to bother. Power save clock gates can be switched off to save in terms of clock skew and the whole time violation. So that is something that has to be handled. Coding style support, I would say, not, it's very subtle aspect. So at a bottom level, you can directly use the same style of coding for both ASIC and FPGA, no problem there. Plugging in FPGA memories. So FPGA memories are different compared to ASIC memories. You need to replace ASIC memories one by one with a similarly functioning FPGA memories. Otherwise, you are going to break the functionality. So this is something that has to be taken care. So this I think I already spoke about before. I will also talk about another important aspect here is basically we have an analog block in an ASIC. So currently ASICs and SoCs comes with a huge, highly capable analog part. That's however not the case for an FPGA. You don't really need to have an analog at all. Analog models need to be a bare minimum because analog cannot be implemented. FPGA is completely in digital domain. So analog functionality cannot be implemented. You need to be able to write a models in such a way so as to fool the digital to think that there is an analog, but in reality there is no true analog. All you need to have is a bare minimum analog functionality so as to keep the digital in normal operation mode out of reset, and the clocks have to be running. So that is something that you need to intelligently do for replacing analog for an FPGA flow. And then you need to have several other behavioral models. Okay, certain models, for example, power management block, they rely heavily on analog signals or analog to digital interface. So those models will no longer work as it is. You need to take care of them, and then you also need to replace, for example, technology specific embedded memories like SRAMs and flash pads and IOSs. They cannot be synthesized as it is. So that has to be stubbed and modeled here. So synthesis, I already spoken about this, is to translate the Verilog or VHDL code or system Verilog code into a schematic format. So here we can have varied goals. It can be area, timing, score, or runtime. So based on that, we need to synthesize. You need to define the goals. You need to define the objectives. You need to define the constraints in such a way so as to synthesize the code into a schematic. So during synthesis, the tool has several switches or several knobs that it can turn to optimize the circuit and then come out with the best possible implementation of the digital circuit that you have just defined. Placement and routing is a crucial part which decides how quick or how efficient your design can perform. So it's going to convert a implemented netlist. It is going to consume a netlist, and then it is going to place each and every map component physically onto the device structure. So that's a functionality of placement tool. It's going to place your logic. If see, the idea is it's going to select the essential hard blocks according to your constraints. So, for example, see block RAMs, clock modifying blocks, and the clock resources, they are given priority one. They are selected based on your constraints. So then it is going to try to map the rest of the design, that is user logic. The rest of the design has to be mapped around that in a way so that the routing is very efficient and the timing goals are met, area goals are met, and then your design is operating in a very efficient way. So these are the different goals that the routing tool will try to chase and close. Finally, the programming part. Once the placement and routing is done, you have a bit stream, you have an image, you have a binary, whatever you call it. It is just a sequence of ones and zeros. It's going to finally be downloaded into the device, and that is going to define the functionality. So this is comparable to the giving life part, right? That I was speaking before. So this is the image that is going to be downloaded. That is going to define and decide how an FPGA will function. So the quality of the design is completely defined by this bit stream. Finally, if you see, this is analogous to the GDS file that we have for an ASIC on FPGA debug. So it's very becomes very essential. It's becomes very crucial to be able to debug the design on FPGA. So, however, please be aware that the debug capabilities or the debug abilities are very limited on an FPGA. You don't have the flexibility of a full-scale waveform like we have in simulation. You need, if at all, you need to probe the design internals in real time. You need to go through the iterative process of synthesis and placement and routing again. You need to identify the signals you intend to probe. They are very limited because again, by adding FPGA debug, you are actually adding logic overhead to the existing design. So you need to handle it carefully because there is a possibility that because of the added debug overhead, the actual design may no longer work. So the debug logic that you have added becomes totally useless. So there are several aspects that you need to balance there. So this in a nutshell is an FPGA design cycle, how it looks like. You have design tree in terms of HDL, and then the functional simulation part, I will say, is a luxury. Not every FPGA design will have this functional simulation active. But typically what happens is you directly go into synthesis, place and route. And netlist simulation is also a enhanced luxury which we rarely have. Then you go back into directly into real time, and then you're asked to debug the design on real time. You need to bring up the design on the real time. That is where the challenge is. So the moment you see that your design is working, that the joy that you see when you see your design is working, and in the blink of an LED, right? For example, you have written a specific logic. Okay, this is my processor, and this is my processor. The processor is quite complex. So this is my processor. The processor, once it wakes up from reset, is going to execute the code present in boot ROM, and then once the booting is successful, he is going to toggle certain LEDs on the board. So the joy that you see when you see that the LEDs are toggling for the first time, it cannot be compared with any other joy that you get as an engineer. So that's when you see that your design is working in real life, in real world, right? So that's the joy. That's what every engineer will look to seek for, or work for. Challenges of FPGA emulation of an ASIC. As I said, I think nothing new here. I have already discussed the concepts before. We need to leave with certain approximations. Of clock network. You need to leave with certain approximations of not having analog. You need to leave with certain inhibitions of limited debug capabilities. So these are the challenges that you need to navigate and still be able to see what you expect to see on an ASIC. So this I think will discuss. So FPGA design skill requirement, right? So FPGA design is a very niche area, I would say. It's not everybody's cup of tea, and it, as I see, right, is an intersection of various domains and skill sets. So it is not that it's a single skill set. It's a combination of several skill set and several backgrounds that you have, that you need to master to be, a good FPGA designer. Let us see one by one. You need to understand the architecture and the systems, because FPGA is not going to work standalone. It needs to be part of a full system. You need to build a full system with collaborating components, interconnects, and peripherals. External interfaces also needs to work. You need to do a lot of judicious, conscious decisions there. So you need to understand the front end design, at least till synthesis. You need to be able to make sure that it's a decent design. The back end skills, synth and PNR, I will say, is on a lower weightage because that's mostly handled by the tool. Then you have software development. Software also you need to have a good understanding. For example, you need to see when in a system, right? It's not just the hardware. You have several, several dynamics coming into play. You have a software. You need to have boot ROM. You need to have firmware also coming into play. So you need to have a good understanding of hardware software collaboration. Hello. Sorry, I'm back. I had a phone call that I could not, resist. It's coming from my company, so I had to receive that. Sorry for that. Let us continue.
Sir, a request. It's already 7:30 and we are in our campus. So could you wrap up as early as possible?
Sure, 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 sure. I want to, wrap up as soon as possible. I think I don't have too many slides after this, so let me quickly go through this. I try to, speed up. If you noticed, the speed of my narration is going up, so I just want to wrap it up. So let me close it as soon as possible.
Sir, could you share your slides, sir?
Yes. Do you see my screen?
Sir, it's visible.
Okay, okay. So this I think we already discussed. This I will skip in the interest of time. So this is a very simple and sample project which I wanted to show to you. I don't know how many of you are exposed to Verilog background, but this is a very simple module block that is implemented using Verilog HDL. So the idea here is to implement a flip flop with a clock, showing a clock and a reset. When there is a reset, the flip flop is going to transmit zero. Otherwise, it's going to the sample the input value, and that input value will be sent downstream. So this is how a circuit. This is how a FPGA netlist equivalent netlist looks like. You can see that this is the flip flop D flip flop that we were trying to write in the code, and that is what has been implemented here. So you see here that there is a clock signal which is coming from external world, is going through an input buffer IBUF. Then it's going to be fed into the clock block. Then you have a reset here, and the reset pin goes to the clear pin. And then you have a D pin. The D pin is fed here, and then you have this output which is going again fed to the external world through a buffer. Okay, so this is the last slide. Talking about latest and greatest trends in the market and in the this FPGA segments, right? So previously, if you see during the early days of evolution, there are several other technologies of FPGA which was in use. It can be fuse, anti-fuse, flash, SRAM, also EEPROM based FPGAs, but all of them have now become obsolete. The only trending FPGA technology right now in the market is SRAM based FPGAs. It's the most popular and is in widespread use. The major players here, just to list here, Actel, Altera, and Xilinx. These are the major players. They, between them, they command more than 80% of market share. Altera is now acquired by Intel, and Xilinx is now acquired by competitor of Intel, which is AMD. Okay, and then when it started, right, FPGA, when it started, I was just quoting before that the first commercially viable FPGA was out in the market in 1985. But now, if you see, it started off as a very basic, next generation variant of CPLD, but now it's comparable with the latest and greatest multi-million ASICs or SoCs that are out there in the market. Okay, it has evolved greatly, as you might be realizing by now. Then it is now being marketed as a full-time replacement for an SoC. Okay, so it incorporates multipliers, it incorporates soft cores. Uh, the moment this feature was added, that was a turning point in its evolution. So then it became very usable for DSP applications. So currently, the most popular use case for an FPGA is to use it as an hardware accelerator in compute-intensive part of algorithm. Okay, so that's where it's coming into picture, so that it can coexist with a processor, or it can coexist with any other GPU to accelerate the hardware implementation and then contribute in a significant way to the throughput and performance. So just to give an example, the device search engine, right? So the search engine Bing have started using FPGAs to enhance their search algorithm, and then to improve or refine their search results. Microsoft Cloud Computing is also deploying FPGAs. Microsoft Cloud Computing is deploying FPGAs for machine learning and deep neural network evaluation. The latest trend in the FPGA market is the embedded FPGA, wherein we are integrating the programmable logic onto the fabric of an SoC. So that's the latest trend that's evolving recently. So we will have an ASIC or an SoC together with a programmable part that can be used to that can be field programmable for various applications. For what all applications, I think that cannot be covered here within the scope of this discussion. So, as a conclusion, FPGA design is a very niche expertise in chip design industry. So, it's a good skill to have. Latest FPGAs are comparable to ASIC in complexity and capability. It's a very popular platform to demonstrate proof of concept and to unlock the potential investments for an ASIC design. It's an interesting intersection of various adjacent IC domains, as I said, verification, validation, software. So there are all these domains are coming into play here to make a successful prototype of a design. Thank you for your time. Sorry, I overshoot the time by some extent, but as I said, right, the subject is quite deep. So, and to do justice to this discussion, I need to go quite deep. So, and as I understood, there are students coming from various backgrounds, starting from a very basic level to some people who have exposure to VLSI design. So, I hope it was useful to all of them. Thank you. Over to you, Naipunya.
Thank you, sir. It was really a very informative and brief discussion about the FPGA technology.
Yeah.
We do have some questions for you, sir.
Yeah, yeah, please.
Sure, sir.
Good evening, sir.
Hi, good evening.
Yeah, am I clearly audible?
Yes, you are clearly audible and I can also see you. Please go
Right.
ahead.
So, the question that I have always had when it comes to FPGAs is the fact that it's very, very vendor specific,
Correct.
right? I kind of find it as a hindrance because if you want, the way I think is, if you want more people to use it and you want more people to want to use it and like even think of it as an option, I feel you should at least have one open standard or something, like for when it comes to programming languages, you have the C standard is open, and then you have multiple vendors who implement it, which is okay. The industry still survives. So I'm just curious, why doesn't it happen, and why has nobody thought about this in the FPGA domain?
It's a very valid point. So it's a very good point that you're bringing up. I think this is a high time that the FPGA players and then the industry of veterans, right, they need to come together and then they need to define, as you said, common standard or way of working. As you said, I totally agree. This is the pain point every FPGA designer has. That it's very vendor specific, starting from architecture to the tools to the way you use the tools, even the user interface, right? It's very vendor specific. You suppose you spend some time working on a vendor on an architecture doesn't mean anything if you switch over to a new product on a new vendor or a new architecture. So that is something that as a drawback I see. Even I totally agree with you. I think it's the time is now right. See, now the computing giants, right? For example, Intel has acquired Altera, and then you have AMD, its competitor, has acquired Xilinx. So Xilinx and Altera were previously unique players. They didn't have that that critical mass to come together and define a common way of working or a standard. But now, since we have these semiconductor giants, Intel versus AMD, together in this field, I think right now that the time is will come soon wherein they define a common set of standards, starting from, as you said, coding. Coding is anyhow it's the it's all HDLs, it's all IEEE standards. But later stages, right? I mean, they should streamline the flow in a way people gain from previous experience to the next project or next experience. I totally agree with you. I think that should happen anytime soon.
Thank you, sir.
Yeah, your good name.
My name is Ram Prakash. I'm
Yeah.
a final year student, EC here.
Okay. Okay. Hey, nice to talk to you, Ram Prakash. You are on mute, I think.
So sorry, sir.
No problem.
Thank you so much, sir, for conducting a session on
My pleasure.
programmable logic devices, and we are really grateful for you. We just hope that you share the slides with us, and we can use it for our future reference as well, sir.
Sure, sure, sure. I'll do it with my pleasure. And I
Okay.
hope the session was useful to you people at least. It was not as if too much was dumped on you in a very short period of time. It's not like that, and I could take something out of this session. Then I'm really happy and glad.
Yes, sir. We really were able to grasp the topics that you covered, and it was quite informative, sir.
Okay, okay, great. So then when I spoke yesterday, actually, you mentioned that the previous presenter was speaking for 2 hours, right? So then probably I got a little bit of the presentation stretched to some extent, but otherwise I could have cut it down a bit.
That's okay, sir. It was really informative.
Okay,
So I would just like to wrap up by telling my heartfelt thanks to Mr. Dilip Rao to in sparing his time to explain us about the various technologies and the budding topics that are there in the field of FPGA.
sure.
Thanks a lot, sir, for conducting this session.
You're most welcome. You're most welcome. My pleasure. So I leave this session. Thank you.